Welcome to this course on digital circuits. So, if we look into this VLSI design process or VLSI industrial development where these integrated circuit chips are being manufactured. So, you will see that most of the designs that we have, so they are digital in nature. So, the basis of all these developments are on this type of circuits where we consider the digital circuits as the building block. So, the start of this modern electronics era, if you look back into the history, so you will see that it started around the revolution started in 1947, where a group of scientists at Bell Labs, they invented the bipolar transistors in 1947. So, 1947 is a very important year for India as well. We got freedom, and similarly on the electronics industry. So, this is another landmark that we had achieved in 1947. So, from that point onwards the electronics design, it has advanced a lot, and today we are at a stage where the complexity of systems and their performance have gone up by leaps and bounds, and now it is almost whatever functionality we think about. So, we look for an integrated circuit chip which can do that one, and majority of them are digital in nature. So, we will see why this has happened. So, if you look into this slide, so in the next in the right side it shows the first germanium bipolar transistor. So, this left side, so this was silicon based on silicon. So, this is the bipolar transistor based on germanium. So, 50 years later, so this electronics account for about 10% of the world's total GDP. So, this is the milestones that we have in the electronics industry. In 1874, Brown invented the solid state rectifier. Then 1906, De Forest invented triode vacuum tube. So, that way this whole development has taken place. So, started with solid state rectifier, then the vacuum tube diode triodes, then the radio circuits, then field effect devices. The patent was filed in 1925. 1947, as we already said, so the bipolar transistor was invented. In 1952, Texas Instruments, they started making these bipolar transistors commercially. 1956, there was a Nobel Prize given to Bardeen, Brattain and Shockley. So, they received the Nobel Prize for this transistor. Then IC was developed in 1958 by Kilby and Noyce, and then the first commercial IC came from the Fairchild Semiconductor in 1961. So, as this industry was advancing, so the scientists also started doing lots of research works, and there was an institution of engineers which was formed IEEE. So, electrical and electronics engineers. So, that was formed by merger of IRE and AIEE. So, IEEE is one of the very popular or societies now that we have, and they, apart from just bringing peers close to each other, they make a lot of standards for the new devices and systems that are coming up, and that way they are helping in the electronics industry. So, whenever we are looking for some development of some device or system, we normally look for some standards, and that standardization is generally done by IEEE, whatever we have today. The operational amplifier. So, this is the analog part. So, though we will not discuss much about the analog revolution, but this analog part also has started getting developed from 1968. So, first operational amplifier IC came up in 1968. The other important part that we have in a system, digital system, so apart from doing computation, so you need to store a lot of information, and in that direction the memory chips, so they are the main part that we have. So, so transistors again are used for making the memory chips. So, this dynamic RAM that we see in almost all the computer systems today, so they were invented in 1970 at IBM by Dennard. So, in the evolution process, as this computations and memory storage, so they went on improving over the generations. So, this computational modules, so they were clubbed together into a structure called microprocessor, where it can do some set of operations in taking help of some registers and some executing some stored program, which it can access through some address and data lines. So, that microprocessor came into 1971. So, it was Intel 4004 microprocessor. So, and now you see that after that it has gone a long way, and today we have got these Pentium processors and other RISC machines and all. So, they are all very advanced versions of these microprocessors. So, this is another digital component that has evolved a lot. Then this commercially memory chips, they started coming in 1978. So, first 1 kilobit memory chip was available in 1978. 1974 another very popular microprocessor 8080 came up. So, this is one of the I should say one of the first well known microprocessor 8080 again from Intel, and that so based on this microprocessor there has been the lot of developments, and all these later microprocessors that are available. So, they are actually developed from this microprocessor architecture. We will see one such microprocessor in this particular course, which is 8085. So, it has it is a bit improved version over 8080. In 1984 we have got megabit memory chip that was introduced. So, memory capacity went up. So, this was because of this we can now store lots of memory, and today storage is not a problem, because these memory chips they have advanced so much, like even these tiniest devices that we have in our day to day life, electronic devices. So, they have got large amount of memory that we can have in the system. So, they can store lots of information. So, that is the point. So, with this memory chip development that is also digital in nature. So, these digital circuits, so they helped us in developing these memory chips and to get the functionality implemented by the systems. Then this another Nobel Prize came up in 2000 by Alferov, Kilby and Kromer. So, they have got another Nobel Prize for this memory and all. So, this way this electronic industry came up. So, after 2000, so we do not have the information here, but as you are all familiar, so lots of development are taking place every day, where this electronics industry is advancing towards better and better processors with higher and higher capabilities and better and higher memory storage capacities. So, if pictorially, so this shows that so this is the first generation where we have got this vacuum tube triodes and all. Then there came the discrete transistors. So, so you see the volumes, the size of the devices, so that has decreased by so much, you see. So, this is a power transistor. So, this is another transistor. So, these are some diodes, some transistors and all. So, they are all discrete transistors. Then after that came this one. So, where we have got this small scale integrated circuits and medium scale integrated circuits, MSI and SSI. So, they are actually these IC chips started coming. So, they do not have large number of transistors in them. SSI chips, they will have about 10 transistors, MSI will have about 100 transistors, LSI will have 1000 transistors, and then VLSI is going beyond that. So, that way we have got large number of transistors. So, today this we have got even further terms like ULSI and all. So, that is actually having larger and larger number of transistors in them. And now this is not a limitation, like if we want to pack large number of transistors on a single chip, that is possible because of the technology advancement. So, we can have transistor sizes very small. So, we can pack large number of transistors on a silicon floor. So, that way size is not a problem, but the difficulty comes in terms of power consumption, in terms of heat generation and all. So, those are of course not part of this course discussion. So, they will go to some course on VLSI design. So, integrated circuit, it was invented in 1958. Then this world transistor production has more than doubled every year for the past 20 years. So, every year, so total transistor production, so it has doubled. So, you can imagine the amount of functionality that is becoming digital every year, digital or electronic, going to electronic components every year. So, more transistors are produced every year, more transistors are produced, which is more than all the previous years combined. So, if you sum up all the transistors that are produced till last year, so this year it is going to be double of that sum. So, that is an exponential growth in terms of transistor production, you can say. So, approximately 10 to the power 9 transistors were produced can be in some recent year. So, though it is not mentioned which year, so it is around that. So, you can roughly 50 transistors for every ant in the world. So, this is another statistical information. So, if you think about all the ants that are available in the world, so each of them that multiplied by 50. So, that gives the total number of transistors in the world. This is just a speculation, of course. So, this is obtained from 2003 source. So, all these figures, so they have gone up significantly by the time today. So, there are a few laws which actually predicted the growth of this electronic industry. So, first one is the Moore's law. It says that the number of transistors on a chip doubles annually. So, this is a prediction and more or less it has been followed. Then there is a Rock's law. It says that the cost of semiconductor tools doubles every 4 years. So, this is another problem, because as the complexity of the system is going up, so you cannot think about designing the system by hand. So, you cannot just take draw say 10 12 transistors, connect them in some fashion and get your circuit design. So, that is not possible. So, we have to take help of these semiconductor tools that may be based on, that may be for this design specification, that may be for simulation, that may be for synthesis, that may be for testing, but the costs are going up every 4 years, because the complexity of these systems are going up, complexity of these chips are going up. So, testing them, the corresponding testing and implementing them, the corresponding tools, so they are also becoming very complex and the cost is going up significantly. Then there is another law due to Macron, which says that the PC you want to buy will always be $5,000. So, what does it mean? It means two things. First of all, it says that okay, the cost will not go up significantly because of the advancement in the semiconductor industry. So, the cost of production will go down. So, that way it is going like this. So, you can say the cost of producing a transistor is coming down. So, that way it will in some senses, so it will balance the cost increase in the tools that you have. So, in the cost of the semiconductor tools that you have. So, that will get balanced. So, if we say on the other side that your cost of this manufacturing has gone down, but what has gone up is the cost of the software. So, softwares are becoming more and more complex. As a result, this the PC will always be more or less the same price. So, if you look at any point of time. Then there is Metcalfe's law, which says that a network's value grows proportionately to the number of users of its users squared. So, that you know very well today in the era of this mobile network. So, you know, so if there are, as the number of subscribers to a network increase, we value that network further, because that gives us connectivity both in our day to day life and social life. So, that way this is another law which says that if you are making the network complex and you can accommodate more number of users, so you are going to be paid back at a square rate. So, that is also very important thing. Then there is Reed's law. It says that software is slowing faster than hardware is accelerating. So, this is another important issue. It says that the software is slowing. So, why? Because the computational power is increasing. So, as a software designer, people think that we can push in lot of functionalities into it, and when we do that, the overall software speed that is coming down. So, so essentially again there are research which will try to make that software faster. So, hardware engineers, they come up with some assisted tools by which you can make this hardware faster to run those operating system and software modules, but it is actually the software which is pulling back the developments in hardware, the speed advancement in hardware to a limit, so that you will always have the more or less the similar type of speed if you are using if you are not using very advanced software. So, this is a reference that talks about this commandments further. So, if you look into the Moore's law, so Moore predicted that the number of transistors that can be integrated on a silicon on a die, so that would grow exponentially with time. So, it says that it will double every year, every 2 years or so. So, what has happened is that it is amazingly visionary law that Moore has predicted. So, you see that million transistor per chip barrier was crossed in the 1980s. So, and then in Ultra Spark 3 had 16 mega transistors, 16 million transistors, and then HP's PA8500 had 140 million transistors. So, that way the number of transistors that we have, so that is more or less following the Moore's law. So, this is the evolution. If you see that this so from 1980 to about 2010. So, if we just look into this DRAM capacity. So, DRAM, how this DRAM capacity is growing. So, you see that this is it was about say 64 kilobit per chip in the around 19 in the year around 1980. So, which was sufficient for holding say one page of information. Then around 1989, 1990, around that time we have got the capacity which is sufficient for a book. Okay. Then in the year 2001, it reached to support, suppose it can hold the entire encyclopedia. So, 2 hours of CD audio or 30 seconds of HD high definition television, high definition television signals. Then then in 2010, so the capacity has increased so much that even the total human memory or human DNA we can store in that chip. So, memory IC is it is becoming 4 times every 3 years, the capacity of the memory chip. So, it is becoming 4 times every 3 years roughly. So, that way it is memory capacity is going to increase. If you plot the number of transistors per integrated circuit, so the trend is like this. So, it started in 1960s. So, if we say that it just started, then it has gone up. So, this Moore's law, which said that the complexity for minimum component cost has increased at a rate of roughly a factor of 2 per year. So, it was later amended to 18 to 24 months. Okay. So, this 2 years, so this was shortened further. So, this was brought down to 18 months also. So, this way the transistor per integrated circuit. So, number of transistors, so it has increased following Moore's law, and that is going on. And as the technology is advancing further and further, so whenever it comes to a saturation point, we see that the technology advances it to the next stage, and this Moore's law still continue to hold in the next generation. Feature size or device size. So, feature size, feature, when you say feature, so it is the size of a transistor, you can say. So, that is the feature size in the VLSI terminology. So, this feature size is reducing, that will enable is enabled by process innovation. So, we in the VLSI manufacturing process, so it is advancing. So, we can produce smaller and smaller sized devices, transistors. So, you can have say something like say 16 nanometer designs now. So, that way it is a big advantage that we have. So, the feature size is reducing. So, overall size of the system is coming down. So, on the same silicon floor, so you can put in a lot of transistors. So, they put more transistors per unit area, and therefore, we can have higher density. So, this is a plot till 2000 predicted up to 2020. So, after 2005, so these are the goals that is set. So, up to this much this was fine, and then it is, so it is dynamic memory interface feature size in micron. So, that has come down significantly. So, So, if you look into this memory chip density versus time, so that is also the density is also increasing significantly as you see over the years. So, that is following a more or less an exponential development, and this microprocessor complexity. So, over this now if you measure in terms of number of transistors, so that is also going up exponentially. So, you see that from 1970s where if you just start around 1975 or so, this 4004 Intel 4004 was introduced, then 1980 this 8008 was introduced. So, like that it went. So, there are lots of developments that are taking place, and they more or less following this Moore's law in the rate of increase of this device density and this computational power. So, if you look into these developments in the electronics industry, so you find development both in the analog domain and in digital domain. So, on the analog domain it is mainly the operational amplifier, introduction of operational amplifier and circuit development around that. So, which has got the momentum. On the digital domain, of course, we have got different type of logic families that are being developed, and we can realize some switching circuitry based on those logic elements, and accordingly we can have some digital design implemented in the IC. So, if you just try to compare between analog and digital electronics, so most observables are analog in nature. So, why do I say so? Because nature is analog. So, there is nothing digital in nature. So, if you look into the temperature, so it is not that temperature is a digital quantity. If you look into the amount of light, so it is never a digital quantity. So, that way so most of the observables that we have, so they are analog in nature. Say weight of some person, so that is also analog in the sense that okay. So, if you measure the weights of different people, so they will be you cannot always say that okay, after say 75 kg, so next weight will definitely be 76 kg or 78 kg. So, in between you can get a number of other values. So, they are the values are analog in nature. Most convenient way to represent and transmit information electronically is digital. So, we will see why. Once we have got it in digital format, so we know that the transmission becomes easy from our say this our devices, electronic devices that we are handling. So, we are normally going for digital designs. So, why did this digital? So, that we will try to explain in the part of this course. So, all the processing job that we do, so they are digital in nature, whereas the nature the environment is inherently analog. So, what is required is that if you are trying to process something in the analog in the something related to the environment. So, we should have this interface which will convert the analog input signal into digital, and again that after processing the actuation should be done in terms of digital values. So, which should be converted to analog value for controlling the environment. So, this way we have got analog to digital conversion on the input side of this digital processors, and on the output side we may have a digital to analog conversion. So, which will convert these digital values to analog actuation signals. So, just to have a understanding, so this analog signal, so suppose we are using this piano and this key A is pressed, so that is of 440 hertz. So, if you so you can represent it in terms of a sinusoidal signal, sinusoidal voltage signal, which has got a maximum volt of 50 maximum peak of around 50 microvolt. So, this 440 hertz 50 microvolt sinusoidal signal may be like this. So, in this side if you plot the time in milliseconds, and this side if you plot the voltage in microvolts. So, the signal generated from the piano key A, so it may be like this. So, on the same time, so if you say that if you are using microphone voltage with soft pedal, then this is it is a 25 microvolt signal, frequency may remain same. So, it is 25 microvolt peak to peak and 25 microvolt peak, and we have got 440 hertz signal. or you can have this piano A, but one octave below the middle A. So, that is about 220 hertz. So, frequency is less. So, this is the peak value is 50 microvolt, and this frequency is going to be 220 hertz. So, this way we can have the analog signals which are coming from the instrument. Now, these analog signals that we are talking about, so they may have very physical relationship to information presented. So, naturally this the direct signal that we have, so they are information versus time. So, this is basically the waveform that is generated is in terms of this, that is giving us some information in terms of the different time instants. So, but it is normally what is done is that we never have these analog signals transmitted or analog signals processed directly. So, we convert it into some other form, so which is known as the process of modulation. So, with the information that we want to send, so that we want to transmit, so is modulated on a carrier such as in amplitude modulation or this frequency modulation, the AM radio or FM radio that we have. So, what is happening? So, this is an example of this amplitude modulated signal. So, here this high frequency signal that we have here, so that is basically the carrier signal. So, we have got this high frequency, this blue colored one. So, this is the high frequency carrier signal, and so this is used for transmitting a relatively low frequency sinusoidal signal. So, if you look into this signal, so this high frequency signal, so this its frequency is much higher, whereas this low frequency signal, so its time period is pretty high. So, accordingly, so if this high frequency carrier signal is multiplied by this low frequency sinusoidal signal, so you will get some waveform like this. So, this is the amplitude modulated signal. So, this diagram it shows the parameters, like see this. So, these parameters of the sine waves, like period, time to repeat, then frequency. So, these are the parameters for any sine wave. So, we can have. So, in this case, so this is the 25 microsecond. So, this is the period of the modulating signal that we have. So, that's the information that we want to transmit. So, that is that period is 25 microsecond, whereas the high frequency sine wave, so its time period is 1 microsecond. So, this is high frequency. So, the period of the carrier is 1 microsecond, that is the frequency is 1 megahertz, and the period of the modulation is 25 microseconds. So, the sinusoidal signal that we want to transmit, so that periodicity is 25 microseconds. So, its frequency is 40 kilohertz, much lesser than this 1 megahertz signal. Then, so this amplitude, so amplitude of this carrier signal is getting modulated by this. So, this amplitude of the modulation is about 50% of the maximum possible value. So, you can just do some mathematics and try to figure out, say, like what is the corresponding equation for this ultimate output signal. So, this is going to be an expression like this. Okay. So, this way we can have this amplitude modulated signal which will be used for this analog communication purpose. On the other hand, when we go for digital signal processing, so we normally use this binary representation. So, this will help us in making the system much more robust. So, we will see it in the next class.